Welcome, class, and welcome to this explainer. I am super excited to be your guide today for the ultimate masterclass on artificial intelligence. We're going to tailor this specifically to help you absolutely crush those A-level Cambridge computer science exams. We are going to break down some heavily tested concepts together, making sure you have the exact knowledge and the precise exam techniques you need to succeed. So, grab your notebooks, get comfortable, and let's jump right in. Here is the game plan for today. We're going to start with the big picture, AMD. Then we'll dive straight into artificial neural networks, have a little story time about backpropagation, look at some real-world AI examples, and wrap it all up with an exam clinic on those tricky command words. All right, section 1, the big picture, AMD. Let's set the stage. So we really need to nail down our definitions right from the start because, let me tell you, the Cambridge examiners, they are sticklers for terminology. There is a classic trap that so many students fall into, confusing narrow AI with strong AI. Narrow AI is just about doing one specific task incredibly well, maybe even better than a human. Think of your email spam filter or a chess-playing bot. Strong AI, on the other hand, is the sci-fi stuff. It's when a machine actually has superior performance to a human across many different intellectual disciplines. Getting this distinction locked in your brain is step number 1. To keep all these subsets straight during your exam, just remember the golden acronym, AMD. It's kind of like a set of nesting dolls. Artificial intelligence is the biggest doll, the overarching concept. Inside that, you've got machine learning, which is all about systems learning without us explicitly programming them to learn. And nested right inside that is deep learning. This is where machines start to process huge amounts of data using artificial neural networks, essentially thinking in a way that's remarkably similar to the human brain. So say it with me, AMD, artificial intelligence, machine learning, deep learning. Okay, moving right along to section 2, artificial neural networks. Let's zoom into that innermost D of our AMD acronym. Now here is a definition you'll absolutely want to commit to memory. Think of artificial neural networks as digital brains. Literally. They're massive networks made up of interconnected nodes, completely inspired by the way biological neurons wire together in our own heads. By handling absolute mountains of data, the system learns to think like a human. And the really cool part? Its performance actually improves the more data you feed it. To visualize how this actually works structurally, I want you to memorize another quick acronym, IHO. It's super simple. First, you have your input layer. That's where the raw data first enters the system. Then you've got the hidden layers in the middle. This is where the magic happens, the deep, complex processing that identifies patterns that would just take humans way too long to find. And finally, the output layer, which hands us the final result. Input, hidden, output, IHO. Which brings us to section 3, story time, backpropagation. So how does this digital brain actually learn from its mistakes when it sees brand new information? It's not magic eyes, it's just really clever math. It uses a fascinating iterative process called backpropagation. Let's walk through the story of how this happens step by step. Step 1, the system looks at its initial output and compares it to what the expected result should be. Step 2, it uses calculus to find the error gradient. Basically, it asks, okay, exactly how wrong was I? Step 3, it takes those errors and propagates them backwards through the whole neural network, tweaking the weightings on each individual neuron to make that difference smaller next time. And step 4, it just repeats. It's a massive system of reward and punishment, constantly fine-tuning itself until the errors are within acceptable limits. The absolute ultimate goal of backpropagation is to hit that minimum acceptable error. It achieves this by essentially sliding down the error curve, constantly, relentlessly tweaking those weights. It bumps them up or down based on that positive or negative feedback until it hits the sweet spot. Let's ground this with a practical story. Imagine you're teaching a machine to recognize a human eye, but you're only giving it entirely unlabeled data. How on earth does it do that? By looking at pixel densities. The deep learning system scans the raw binary code of each pixel. It takes a blurry, meaningless image, runs it through its neural networks, and constantly adjusts its internal weights using backpropagation. It does this until, suddenly, it spots the pattern, and that blurry mess becomes a perfectly recognized, crystal-clear image of an eye. All right, section 4, real-world AI examples. Time to take these textbook theories and see them in the wild. Cambridge examiners absolutely love it when you can connect theoretical definitions to actual real-world applications. So here's a quick cheat sheet for you. Think about chatbots. They simulate conversation using predefined scripts and machine learning to figure out human interaction patterns. Then you have face recognition, something you probably use to unlock your phone every day. That relies heavily on deep learning to precisely map out facial node distances. And what about web crawlers? They systematically browse millions of unlabeled web pages to categorize them. This is a classic example of semi-supervised active learning, using a tiny bit of labeled data alongside an ocean of unlabeled data to save a ton of time and money. It's honestly amazing how vastly different technologies share the exact same underlying principles. Whether it's facial recognition software measuring the precise distance between your eyes using neural networks to spot patterns, or complex autonomous systems like self-driving trains and robotic arms, they are all taking in massive amounts of input data, crunching it through those hidden layers, and making split-second, incredibly intelligent decisions about their physical environment. Now for the most important part of today's explainer, Section 5, Exam Clinic on Command Words. Listen up, guys, because all this incredible knowledge won't get you top grades if you don't know exactly what the Cambridge examiners want to see. Let's look at the command word analyze. When you see analyze on your paper, please do not just give a simple summary. The official requirement is to examine in detail, to show meaning, identify elements, and, crucially, explicitly show the relationship between them. You absolutely have to connect the dots. So let's say you're sitting in the exam hall and you get this mock scenario. Analyze the impact of implementing an AI chatbot on a company's customer service platform. How do you build a bulletproof full marks response? Let's break it down using the exact methodology we just discussed. You'd structure it step by step. First, define the tech. Boom. State that a chatbot simulates conversation using machine learning. Second, identify the elements. Mention that it relies on predefined scripts and neural networks. Third, and this is where you secure those top marks, examine the relationships. Explain exactly how iterative processes, like our friends back propagation, allow the bot to learn from user inputs and actually improve its accuracy over time. Finally, link it all back to the impact. Connect that fast processing to a measurable boost in customer service efficiency. That, my friends, is how you truly analyze. Now, what if they hit you with evaluate? Totally different ballgame. Now you need to make a reasoned judgment on the quality or value of the technology. For instance, you might talk about the unbelievable processing benefits of deep learning, but then you have to weigh that against a huge drawback, the black box problem. Because these systems make decisions based on insanely complex logic, hidden deep inside those middle layers, the actual reasoning behind their choices can literally be impossible for a human to interpret or understand. And that brings me to a final, really crucial point to ponder, both for your evaluate questions and honestly for your future careers. As these artificial neural networks become incredibly complex black boxes, making rapid-fire decisions on everything from driving cars to diagnosing medical conditions, how will you, the next generation of computer scientists, ensure those independent decisions remain ethical and transparent? It's a massive challenge. Think on that as you review your notes today. Thanks for joining this explainer. Keep practicing those command words and go crush those exams.